data that you just collected, I know you could all graphically analyze the results, but before we graphically analyze it, let's get a sketch, okay? So a sketch. So first off, what should the axes of your graph be based on this experiment? So did you guys use concentration? Use milliliters technically, but in the real world with equilibrium, we'd be using concentration. So milliliters of water, okay, and then over time. Good. So I'm going to do A in red. Okay, so you want to make a legend like A is a dashed line, A, B is a solid line, or something like that. At the very beginning of this reaction, what did you have? Huh? 25 milliliters of A, okay? So let's put 25 milliliters up here, and that's what you had of A, and then what did you have of B? 0, right? So at time 1, you had 0 of B and 25 of A. Okay? At time 2, I know some of us had some spillage going on, but what should have happened to A? It should have decreased by some amount of milliliters. So some of you guys had a really good suction, so maybe it's like 2 or 3 milliliters. Some of you guys had crap, so it was like half a milliliter or spilled half, and then the rest was maybe transferred. But over time, what should be happening to A? Slowly decreasing, right? And slowly to B, it should be what? Increasing, right? So at time 2, maybe it was here. Okay, and then time 3, it was here. Okay, and I don't know what your data would have looked like. Like, I don't know if B would have surpassed A or not. It does depend on which is the favorable reaction. Well, we're talking about water here, so it is a very hypothetical situation. But I'm going to go ahead and connect my dots, because what we should have started to see at some point in time in the process, B was going to start to stay constant, because every time you transferred A and B across each other, you're transferring the same amount, the same amount, the same amount, the same amount. Okay? So eventually we would have had A staying constant and B staying constant. At this point, what have I met? Equilibrium, right? So the idea is that A decreased over time because A is a reactant. But at some point, A is going to be stagnant, and B was a product. So I started with all reactant, no product. Slowly, the product is produced as the reactant is consumed. The product is produced as the reactant is consumed. The product is continually produced, but overall, is there a net change in the concentrations? Yea or nay? 3 people said no. Is there a net change in the concentrations at these points right here? No, because there's no change there's no slope change. It's a 0 slope. So there's no net change in concentration at equilibrium. So what we have to now kind of realize is that we actually know this. We knew this graph already. We've seen it before, but we actually only saw the first half of it. We saw concentration versus time. Okay, that was very familiar to us. We also saw reactants decreasing over time. That was what? This was the study of what? Change in concentration over change in time, guys. What is that? Rate, right? So that's rate. So we already knew that. So we've talked about the first part of this, actually, a whole lot, the whole unit. But now we're going to talk about the last half of that graph. Come on. Let's go, Megan. All right, Megan, you got this. Woo! I am your only cheerleader, apparently. Okay. Grab whatever paper you wish. Okay, so knowing this, can you guys start answering questions on 1? Yes, go. This is on your paper.
Please pardon the interruption. All students going on the field trip with Mr. Vargas and Mr. Dale will be in the comments at this time.
Answer this question. On 1, give me a quick answer. Volume or 1I, volume of water in cylinder A is what? Concentration of reactant A. B, 2. Concentration of product B. Okay, transferring A to B. Reacting in the forward direction. Number 4, transferring B to A. Reacting in the reverse direction. And then the total number of transfers. Total. So the number of transfers is just like we reacted. So I wouldn't say it's a total number of reactions because like this continues. We just stopped at some point in time. It's just the duration of the reaction, right? It's just time. Okay. By observing your graph, describe the changes in volume. I think you guys got that. We never made it to this point here, but I'll tell you what that addition is here in just a second. I'll highlighter here. So at some point in time later on, and once we got to equilibrium, it said to add 2 milliliters to, I think, cylinder A. Can you look on there? What did it say? What is to A? 1 milliliter to A. Okay. So A is our red line here. So at some point in time, it says to add a certain amount of reactant. So we're going to add it here. Need that. Okay, so we're going to erase that space. So we're going to add a little blip in our graph. Okay, so it's going up. Eventually, though, what's going to happen over time again? It's going to go back down. Okay. That looks like it's a little lower. I don't want it to be lower. I want it to be a little higher. So it's going to go back down, but it's not going to be lower than the initial original reactant. So what's going to happen to B at that point? It's going to go up because as soon as reactant A goes up, B's concentration as reactant A reacts is going to go up a little bit, but it's not like a peak. It's kind of like a hump. Okay, and then it's going to level out too. That's not level, but that's level. Okay, so that's kind of what CJ, it's right there, back the middle last station. Grab for your response. Okay. Okay. And then can you guys do 4? Yay or nay? So I did not make the 2 meet, and that's simply because I made up our data. Okay. But if they were to meet like this, if they were to meet, what would that meeting place be? Drew, it's right there in the middle last station. Grab paper and grab your response. What would this be? That would mean that they're equal what? Equal concentrations just by chance. That means reactant concentration equals product concentration. But is that always true at equilibrium? No, it just means concentrations, reactant, and product stay constant. It does not mean that they're equal. This is the case if they were touching, they would be considered equal. Yeah, let's hold off on this number 5 for a second, okay? So we got to talk about what stress is after we talk about today's lesson, okay? So put that lab to the side. I wanted you to see this for a moment before jumping in. I see it worked out fantastically, okay? I will do this in the future. Okay, so let's connect the dots on some things that we actually already have learned, and we eventually will get back to our packet. It's going to be a minute. When we talk about thermodynamics, we talk about connect, we talk about equilibrium. They do have something in common, but there are some very distinct things that each of those concepts tell us. One, thermodynamics. What variable tells us if a reaction is spontaneous? G, good. So, if G is what sign? Negative, it will mean the reaction is thermodynamically favorable. But that just means, hey, this reaction is going to happen without intervention. That's all that means. Does it tell us anything about the rate? Does it tell us which reactants or products are favorable? Yes, it does. It does. Okay, so every time we've mentioned G so far, we've been talking about the forward direction. So we've never necessarily considered just focusing on the reverse reaction. So everything we've discussed so far has been forward directions. Last unit we talked about like, hey, there's this thing equilibrium, but we're going to talk about it more now. So if delta G is negative, so it's favorable in the forward direction, which do you think it's showing as favorable, reactants or products? So is it wanting to form reactants or is it wanting to form products? It's like, hey, I want to form products. Probably because products are more stable. So there is a connection between thermodynamics and equilibrium, because if something is favorable in the forward direction, or thermodynamically favorable, that means the products are favored. That means the products are stable. That means that there's some energetically favorable condition the products are in, but the reactants are not. So there is a connection there. Okay. Kinetics, we know that it gives us the expression of rate. We have been mentioning that there are two versions. Ricky, the first one's right there in the middle. Grab some papers here, okay? We have mentioned rate forward, and we have mentioned rate reverse. So we know that we can reverse the reaction. We can talk about the expression and the activation energy in the reverse reaction and so forth. So it basically just tells us how fast the reaction is going to occur. Does this one tell us anything about favorability? Darcy's confident. It does not. It does not tell us if the reaction forward or reaction reverse is favorable. But what we know now with equilibrium is that we need to know something about rates to determine when reaction is at equilibrium. What is true about the rates once we're at equilibrium? I'll say they're first, somebody said they're first equal, okay? And you're right, they're constant because I'm forming products and reactants at the same rate. So you're right to say they're constant too. But this is now true at equilibrium. So we're starting to see there's some minor connections between all the units we've studied. Now, what is equilibrium? It's kind of weird. You do have to know that the rates are equal and concentrations are unchanging, but it just tells us the extent of the forward reaction. So if a reaction produces a whole lot of products, that means the K is very large. This is a capital K. This is not a lowercase k. Lowercase k represents what? Rate law constant. Capital K means equilibrium constant. Okay, so we know our capital T's, lowercase t's, capital K's, lowercase k's, and so forth. So if the reaction makes a whole lot of products, the extent of the reaction is very large. The K is very large itself. What did we correlate to a large K in thermodynamics? Favorability of the products, negative delta G. So that's what I was saying earlier. There is a connection there, but I had you guys, do you remember that equation? Delta G is equal to negative RT ln K. We're actually going to use this now. Okay. I want you to notice there was a connection, but you didn't know what equilibrium was yet. Okay, so those are some of the background pieces. We're going to go forward. This is a review of the reading guide. I'll get to that shortly. So the very first thing that I always start with is just the easiest form of equilibrium. It's phase changes. So we know that there's such thing as physical equilibria and then chemical equilibria. Physical equilibria is just when we are at the phase change point, and let's use this example here. One molecule of water is going from liquid to gas. So what phase change is that? Evaporation, vaporization, and then one gaseous molecule is going in the reverse from gas to liquid, doing what? Condensing, right? So that's happening constantly in a closed system. So like this is my closed system here. So if something is boiling, or like in a water bottle and it's warming up, maybe out in the sun, you're going to see a little condensation appear on the bottle, the top of the bottle. And that's because there's this constant cycle of evaporate, condense, evaporate, condense, evaporate, condense. So what we're saying is that it's in physical equilibria because I'm not forming more gas than liquid. I'm forming the same amount of gas and the same amount of liquid, but it's happening simultaneously. So this is the rate of forward equals the rate of reverse. But you guys told me the phase changes already. The rate of evaporation equals the rate of condensation. So that's only going to happen at the moment phase change begins. The other one that I want to make sure you're aware of is that aqueous solutions can be in equilibrium with themselves as well. So if I have a solution, and it's an an aqueous solution and I have sodium chloride, for example, being dissolved, it will be producing ions in the forward direction and then reverse, so precipitating itself back out in the reverse direction. So it's an equilibria where we have ion or solid ionizing and then ions solidifying or crystallizing. And so it's a constant equilibria. So we will eventually get to the point where the ion concentration is constant because for every ion produced, there's one precipitated. Every one produced, there's one precipitated. So this physical equilibria makes sense. It's just a weird concept. It was just like, we just say when something stops dissolving, we say it's at equilibrium with itself, but it doesn't actually stop dissolving. It's a dynamic process. You guys saw the word dynamic in your reading. What's dynamic mean? Constantly changing, but overall is there change? No, so it's dynamic equilibrium. There's a constant changing environment where there's no net change. Because like net would be like if I gave Niall $10, he gave me back 7, what was his net gain? 3. So that's the overall change. Okay, so my little highlights have changed. Woo. Changing from home to here doesn't always like smart word. Okay. So what we've seen now is that we have a lot of reactions with a single arrow. That just means that we have a 2 completion reaction. So that's what we've dealt with most of our chemistry labs so far. And when we have a completion reaction, it's generally a limiting reagent. So we have one of these reactants that 100% get wiped out, but we're making 100% products. So it could be like an LR problem. But overall, we just know that we're making 100% of a reaction occur, which means we're going to make all of the products that we possibly can. But now we're going to start to see the reversible arrow, which means that we can have, we won't have a 100% reaction. We will have leftovers, leftover reactants, and some other products produced themselves. So we'll have some reactants left and some products made, but there won't be one or the other wiped out. So those are just 2 examples here. And the example below with the blue and green down here, don't feel like you need to write this down. I'm going to have more examples that are calculation based in a second. But the idea is that you can start with all reactants or all products, and they will react in the in the forward or in the reverse reaction to get to equilibrium. So it doesn't matter where you start. This process will achieve equilibrium eventually, because that's what its chemical stability will tell it to do. So I can start with 0.7 mole or 0.07 moles of nitrogen dioxide. Eventually, it will form this amount of nitrogen, or leave left over 0.06 or 116 moles of nitrogen dioxide and make that much dinitrogen tetroxide. Or I can start with like half of the dinitrogen tetroxide, and eventually it will get to equilibrium and form this amount of reactant product. Do you notice that these are the same numbers? So it doesn't matter if you start with all reactants or all products, eventually it will achieve equilibrium. And so we can calculate the KEQ for this reaction, or the K, just the K is called the equilibrium constant, or KEQ is just another version of writing that. Can you tell me which side is favorable, reactants or products? Why do you say products? Right. So in both situations, in the first situation when we started with all reactants, it formed more product overall than reactant left over. And the second situation when we started with all product, it ended up still yielding more, or leaving left over more of itself than the reactant made. So overall, this K is what? Greater or less than 1? Greater than 1. So greater than 1 means products are favored. Now, we don't have to just memorize that. There is a mathematical reason behind it, which is the K constant calculation. We're going to get to that in a second. Thumbs up if I can move on. Conceptually, are we okay so far? Most of us are not shaking heads. Okay, great, guys. Okay, so we know that just like in a lot of systems in chemistry, there's homogeneous systems and heterogeneous systems. Homo means what? Same, so we're talking about the same phase. Many times these are gaseous. So if they're gaseous, a lot of times that'll be called gaseous equilibrium. And gaseous equilibrium can either give us partial pressures or concentrations. So if they give us partial pressures, we would find the Kp, meaning for the pressurized system itself. And if they give us concentrations using molarity, we would find the Kc. Those are not interchangeable. They're just representing equilibrium using different units to input into the data. So if it was Kp, we would find the Kp. And if they gave us molarity, we would find the Kc. But these are still both equilibrium constants. There is a relationship between those two. Did you guys read about that? The politically correct formula? Okay, we'll read that too. So the formula was the same. Heterogeneous means just two different phases. You can see what's happening in this process here. Example, calcium carbonate. What type of reaction is that? Nah, I know it's got a double hit error, but what are the 5 types of reactions? Like old school. What is this? Decomp, right? So a decomposition reaction, if we could contain it in a closed container, the gas would not be able to escape, and eventually it would reverse itself, and we could get a reversible reaction there. So that's just a decomposition reaction, but we have solid-solid gas. KSP, barium sulfate is a solid precipitate. It can, with itself in solution, undergo ionization, a very, very, very small amount. You know how we always say, like, oh, precipitates don't dissolve, right? Period. They solidify, they hit the bottom of the container, that's it. That's a little bit of a lie. Some of them do dissolve just a hair, but we don't really see it because we still see the big white clumpy precipitate. But like this does dissolve a little bit. It makes Ba2+ aqueous and sulfate ion aqueous. So you'll notice we have solid aqueous. That would be a heterogeneous equilibrium condition. So that's why I just say two different phases. The aqueous does count as a separate state. Okay, so we kind of already talked about this. Gaseous, a lot of times we'll use partial pressures. We'll review that again shortly. And if they're aqueous or, yeah, if they're aqueous, pretty much that's the only other time. That's the only time we would have molar concentrations. Because what is molarity again, units-wise? Moles per liter of solution. Okay, we do not use molarity unless it's an aqueous solution because that's the only time we have a liter of liquid to throw stuff in. And then we'll talk about these whenever we get to those. Acid-base equilibrium as a whole, like unit in itself, but we will talk about precipitates maybe on Thursday. Okay. Thumbs up, can we move on? Okay. Draw a quick graph of something at equilibrium. Let's see where you go with this. Doesn't have to be pretty, just a quick sketch. And then compare yours to people around you to see if you do yours similar. Alright, so I see already 3 different graphs, and they're all valid. I see 3 different graphs, they're all valid, okay? So please, like, I don't know if one's right. As long as you hit equilibrium, meaning constant rate, you're good, okay? So some of you get started with reactant concentration high, you went really low. What happened to product over time? Products, let's say we start with 0, you went increasing, you cross the lines. When you graph it like this, it shows you one thing very clearly, which is favored, products or reactants. Products are favored because their line's on top. Okay, and we're at equilibrium about right. That right there looks to be when the rates stop changing, or the concentration stop changing. You also could have done, can I erase this? Yeah. It depends on the reaction. It just depends on if K is going to be greater than 1 or less than 1. Well, it's significant because it tells you the favorability, but there's no way to tell unless you have a scenario. Okay. You also could start with no reactants. This is the reactant one, and then a bunch of products, and let's say they never cross. Well, yet again, who is favored? Products is the line of concentration of products is higher than the line of concentration of reactants. but I've met equilibrium, yeah, about there, because at that point the concentrations look like they're not changing. And then I had one more I saw, which is a very rare situation, but it's where no matter if this is reactants or products, no matter if this is reactants or products, where they merge. And that's very rare because actually at this point product concentration equals reactant concentration, but we've met equilibrium about right there. Okay, so that's very rare. Usually we see one of these. Okay, so I like to say it's still frantic because remember it's still dynamically changing. Reactants are being formed, products are being formed, but at the same, they're happening simultaneously, so there's no net change. Yeah.
When you say it's rare, is it because like it's hard for the moment it used to be exactly?
It's just very, there's a low possibility for reactants and products to be the same concentration because the scenario would have to be like when K equals 1, neither products or reactants are more favorable, and it's very odd to have both of them in the exact same thermodynamic stability. So that's what it means. Okay, so we see we can also see stoichiometry in these graphs. Look at the reaction, look at the graph, and tell me how you can see the stoich in the graph. Talk to your partner first. Yeah. Okay, give me a hand. Who can tell me how you can see the stoich from this reaction? Taz, get me started.
Well, I said that the product is NH2, reactants are H2 and F2, and that H2 is really favorable, so I don't know if the product is.
Oh, you mean it's favorable, meaning there's more of it at equilibrium, okay.
So I said H2 would be favorable, but the reactants overall, I don't know if they would be favorable.
Well, you're talking about favorability. I want to know about stoichiometry.
Never mind.
Let's pick up from there, William.
It's like your initial concentration of H2 is very high and everything's high because of the
Nope. But there's a 3. Okay, so let me pick your brains a little bit more. Do you see the rates of change are different? Okay. Why are they different? Because the coefficients. Okay, so who's consumed 3 times faster? H2. Okay, so you see it's declining. It's a very, very steep decline compared to decline of who? Compared to the decline of who? N2. Okay, so it's about 3 times faster declining versus N2. And then it's maybe a little difficult to tell with my line right there. Can you see that NH3 is formed at twice as fast as N2 is consumed? Okay, so we can see the stoich at first, and then we don't care about the rates of reaction anymore. We care about when they meet equilibrium, and that's the time at which they meet equilibrium. But you can definitely still see the stoich if you have the full graph. And most of the time we will have the full graph because nobody just says, hey, here's equilibrium, this is all you need. They're going to give you the whole shebang. Or you'll have graphed it yourself. So, this is just another scenario like I had verbally. If I give you an initial reactant or I give you an initial product, no matter what the conditions at a given temperature, equilibrium will be established. So for the H2 plus I2 yields HI, this is the reaction. Eventually, they get to the point where these are the reactants, they react, they go away, products get produced, they go to equilibrium. You'll notice they're the same if I started with all products and no reactants. So it doesn't matter where you start, equilibrium will be established. Yet again, who is favored in this reaction? It's the product HI, right? And I know this is flipped here. We never, ever, 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 ever flip our reactions. It's just showing you the reverse reaction. You will always see for us this reaction still. It's just representing the reverse that's occurring because you're starting off with the product. That's how we would still represent it. Okay, so please read this. Make sure you know this. Write down what you need to. I think I've said this 5 times at this point. There's probably not a whole lot you're writing down. Just all you're reading too. I am trying to make sure I'm detailed here because I know some of us had like 2 seconds of equilibrium like 2 years ago, or no equilibrium last year, depending on which teacher you had. It's very minimally in honors form, so make sure we're clear. And we always do establish these in closed systems, because if I had an open system, products could escape or reactants could escape. If they're gaseous or even if they're aqueous, they could precipitate out and water could evaporate. So we always have a closed system to maintain that particles that are there, and they're not shifting equilibrium around. So occasionally you'll see double head arrows like this. If they're the same magnitude, it means that both forward and reverse are favorable. If we see double-headed arrows like this, what does that tell you? The forward reaction is more favorable than the reverse. And if we see like that, reverse is more favorable than the forward. Okay. Oops. Okay, so just as a connection, one more time to kinetics, and then we'll stop with kinetics for now. This is a reaction, concentration of A, or A yields to B, it's reversible. Technically at equilibrium, what's true about the rates? They're equal, okay? Rate forward equals rate reverse. So what I can do is I can set rate equal to rate, but I don't really care about the rates themselves. I care about the products and the reactants now. In kinetics, we only dealt with what? Reactants or products? Reactants, reactants, reactants. We didn't care all about the products. Now we care about the products too, which is why I did not want my people to take the test after seeing this, because then people start writing products and then I start yelling at people, and I don't want to do that. Okay, so this is the forward reaction forming B from reactant A. This is the reverse reaction forming A from reactant B. So I've just set them equal to each other. Okay, I want to consolidate the K's, the rate law constant K's, in the concentration. So all I'm going to do is just divide. Okay, so I get B over A. Why is that relevant to what we're doing today? Concentration of B over concentration of A. That's how you write the K constant. You do products over reactants, right? So there is a relationship between the forward and the reverse direction. It's concentration of B over concentration of A is equal to this rate law forward over rate law reverse. But the whole idea is that we're not using rate laws anymore. We actually take this into consideration as we determine the value of equilibrium constant K. That's all background though. We don't do that ourselves. We don't calculate the K like that ourselves. How do we calculate K? What do we set up for the K expression? This is equilibrium constant K. Who goes on top? Products or reactants? Products. I'll do the general expression of C to the, this is ugly, hold on, let me fix that. C to the little c power times D to the little d divided by A and B. Okay, you saw this as the generic K expression. We will all, because usually in our data, we're not going to be given rates anymore. We're not going to be given equilibrium, we're not going to be given rate constants or anything like that. We're going to be given concentrations at equilibrium. If we're given concentrations at equilibrium, we plug it in here, and that's how we solve for our K value. Okay, so I have a slide on this next. Now, what are these, I know you guys read this, what are these little C, D, A, and B values? They're coefficients, and then the big C, D, and A, and B are all just the reactants and products. Okay, so there's that right there. The whole theory behind this, some guys came up, they called it the law of mass action. It doesn't really help us at all, but you should know it's called the law of mass action. And we will only be plugging in what types of substances into these. Gases and good aqueous solution. No what? Solids and liquids, because over time, I'm looking to see eventually how concentrations potentially could change over time. Do solids Do solids have a molarity? No, because that would mean the solid moles per liter solution, it would mean that would have to be aqueous. And that's when we don't use pure solids. We have to say S to that. Next to that, we would not be using those. And then pure liquids, do they have a molarity? Like, can water be pure liquid? Yes. Can water be aqueous? No. Water can be aqueous because it have to be moles of water over liters of what? Because water itself is not going to be in solution, it is the solution. So water can be pure liquid. So we would not be using water because water's concentration does not change because it doesn't have a concentration necessarily. It doesn't change appreciably. Oh, I hate that. I saw that. We can get into a large conversation about that. Okay. Okay, so knowing the C, little c here, that just means concentration. That means molarity. What does this P represent? Partial pressures. So I want to write this the same way, but using partial pressure notations. So this will be P of product C, no brackets, okay? Brackets are only used for molarity, raised to the little c power, or the coefficient of C, times partial pressure of product D, to the coefficient of little d power, over partial pressure of A, raised to the little a power, times the partial pressure of reactant B, raised to the little b power. So, if we're given pressures, like what would clue us in that we're given pressures? It would say like atmospheres or millimeters of mercury, whatever, right? It would give us pressure units. And they gave us molarity, it would give us molarity. Or sorry, if it gave us concentration, it would give us molarity. Okay, so essentially what this overall means is just the ratio of products to reactants at equilibrium. So the only values we're plugging in here are equilibrium values. So would I be plugging in values from here? Here? No. Here? Yes. Okay, so it's got to be at equilibrium to be plugging those values into this equation. And then, as you know, we've been saying products are, the favorability is indicated by the K value. How in the world does K become large? Which numerator denominator has to be bigger? Numerator, which represents products. So if products are favored, there's a lot of them, right? Naturally, the numerator is larger than the denominator. K is greater than 1. So mathematically, this is really, like, you don't have to remember the concept, you have to remember the math. And if, let's say over here, I had a lot more reactants than I had products, what happens numerically? You're having like a small number over a big number. The big number wins, right? So this makes the number, it becomes driven down, so the K value is less than 1. So the reactants are favored because you have more of them. So mathematically, it should make a lot of sense. Okay? Okay. Already talked about that. Do not include pure liquids and solids. Deal? Deal? Shake on it? Okay. All right, so I want you guys to write the K expressions. When I say K expression, I mean Kc equals blank over blank. Kp equals blank over blank. I want you guys to do that for these 1, 2, 3, 4. Go. Try it. You know the rules. first one, what you guys got? So concentration, bracket, CO2, right, that's it. I wouldn't even put over 1. Because then, at one point in time, College Board did not accept that. I just try to make sure you're getting your points where you need them. Because they thought if you put over 1, they thought you meant the concentration of calcium carbonate mattered, and it doesn't. Yeah. So it depends on what data is given to you. If concentration data is given to you, plug in concentration. If partial pressure data is given to you, plug in partial pressure. So I was going to say, or you could put it as Kp is equal to P CO2. So it does depend on what data points are given to you. I didn't put C, or I could just put EQ there to be cheap and just put any of them. But if I put C, I put concentration. If I put P, it's partial pressure. Next one, let's do Kc is equal to NH3 to the second power divided by bracket H2 to the third times N2 to the first. Good. Next. Kc is equal to NH3 over H2 to the 3/2 power, right? You can't put fractional or exponents times N2 to the 1/2, also known as square root, right? Okay, you could put like square root. Yeah.
There's a word genius, like, the word genius is specified in these gaseous.
If it's heterogeneous and it gives you all concentrations, you better be using Kc's. If it gives you a partial pressure, or if it's heterogeneous, you can't use Kp because they would all have to be gaseous. Okay. Most of the time we're using concentrations. That's why I'm focusing on this now. Okay, next one. Kc is equal to. So this is steam, right? Not liquid. That's why we're using water. And times concentration of CO2 over. Somehow I have miraculously made gaseous baking soda. Oh, sorry, it's the second power. Thank you. Okay, I was still wowed by my gaseous baking soda there, but that is not a thing. Okay, sometimes you know when I make good examples. All right, can I move on? Products of reactants, no solids, no liquids, we're done. Okay, so we keep saying what K means. Please write down what you need to, but there's some words up here that I'm not explaining yet, so read first and then we'll talk. So lies to the right just means products are favored, K is greater than 1. Lies to the left, K is less than 1. Very, very large, though, could mean a completion reaction. Just note that to yourself, because if we have a whole lot of products, that's going to be like, you know, a billion concentration. If you had a lot of products, you could have a lot. Over 1. Then essentially we would say, I know it's not to completion, but we would say it's going to completion because there's so many more products and reactants. And if your value of K, let's say, was like 1 times 10 to the negative 40th, very, very small number, right? We wouldn't say the reaction did not occur. We would say the reaction does not occur appreciably because it does not occur very much. That would be something like a solid precipitate dissolving. Because we don't see it happening, but we know it does just a wee bit. If the reactions if reactions forward and reactions reverse are tending to occur in equal amounts, because the energy, the stability there shows that both are equally, both reactants and products are equivalent energetically. Do you know what I mean by energy or energetically? Any guesses? Something about spontaneity, something about its thermodynamic favorability. So if they both, if forcing production forward or production backwards gives you a delta S somehow that's positive, and a delta H that's negative, a delta G is negative. They both could all be this, but there was some sort of equal favorability, then it could still yield a K of 1. And we've said this like 3 times now. I don't know if you've written this down. K is temperature dependent. Just like rate law constant K was temperature dependent. Remember, big K is kind of a conglomeration of both of those little K's, forward and reverse. Yet again, itself is still temperature dependent. There's only one value of K at each temperature. So if you had a reaction that was exothermic and you heat it up, it will change the K. If you have a reaction that's endothermic and you heat it up, it will change the K. We will get into that, but we're not going to just for the moment because we're not done with even calculating it. So my example is done here. I'll get to you later. Okay? Can I move on? Gigi says yes. Okay, I'll wait a second. So far, we know what K is. We know what equilibrium graph looks like. We know how to write the K expression. We know K big and K small. Good? We don't know a whole lot yet, but we're still getting further. Okay. So, do you remember in Hess's law, if we multiplied a reaction by 2, what did we do to delta H? We multiplied delta H by 2. We said, okay, whatever we did to the reaction, we did exactly the same to delta H. Is that the same case for here? No, we manipulate it very differently because K is a ratio of reactants to products. Delta H is like, hey, here's how much energy I release or consume. They're 2 totally different things. So keep delta H's in its own place, keep K's in its own place. So if you ever take a reaction and you reverse it, you've essentially just taken the products and made them the reactants, and you've taken the reactants and made them the products, right? So does that make sense why we flipped the K? Because you flipped the numerator and denominator. So that's why if we reverse the reaction, we inverse the K value, or the K value or the K expression. So if I had 100, K was on 100, and I flipped the reaction, what is K? 1 over 100, right, which you calculate to be 0.01. Okay? If you take a reaction and you have a multiplier of sorts, like either multiply by 2, multiply by 3, multiply by half, that is now adjusting all the coefficients, right? Do the coefficients matter in K's? Yes, they become what? Exponents. So whatever you did to the coefficients, you're doing that to the exponent. So if I multiply something by 2, I square the K, because I have essentially made all the coefficients 2 times greater. So then I'm squaring those K's. If I multiply by 3, I cube the K. If I multiply by half, what do I do to the K? I square root the K, because that's raising it to the 1/2 power. So you manipulate it very differently here. If you add up reactions, so some reactions, then you're going to you're going to multiply the K values, because we're taking a certain number of reactants and a certain number of products, and we're kind of piling them together on numerator and denominator, and everything in numerator is multiplied, everything in denominator is multiplied, therefore we are multiplying the K's. Okay, so this example is on your notes. It's the very first sheet. You can pull that out. I got about 5 more minutes. I'm going to try to knock this one out and maybe one more slide. Okay. So what is the K expression for this first reaction, or this first example? Concentration, nitrogen dioxide to the first power divided by N2O4 to the 1/2 power. Okay. What is the second expression? N2O4 to the 1/2 power over, okay, went ahead and before I even wrote these down, I think you could have told me, what did I do between reaction 1 and reaction 2? I reversed it, right? So this is the reverse. So what did I, now that you can see them over here, what did I do to K? I went over it or I inverted it, okay? Because of the nature of how products and reactants are stacked. So, we know how to do that. If I wanted to, I could have said Kc prime is equal to 1 over Kc, just to not even plug in the data points, I could just plug in the Kc. Okay, what do I do down here when these reactions are, I want to know the Kc value for this final reaction. Do you see the relationship between this and these? What's the relationship? It's the summation, good. So we see, so it's the summation, right? So remember, just like in Hess's law and in mechanisms, what could we do to reactants and products? When we add these up and there's something on both reactant side and product side, I could sum them and cancel. So what am I canceling? Okay, anything else? Nope. Okay, so this stays, good. 2 H pluses come down, and then oxalate ion comes down. All right, so technically, what do I do to my K values? Well, no. Okay, so remember, summing reactions, what do I do to K values? Multiply K values, if I can write today. Okay, so I'm going to multiply these two. Okay, so what's 6.5 times 10 to the negative 2 times 6.1 times 10 to the negative 5? Let's just do this in our head. What's 6.6? 36. I know this is lowballing it, but 36. What's 10 to the negative 2 times 10 to the negative 5? 10 to the negative 7. So like something like 3.6 times 10 to the negative. So move that way. Negative 5th, right? I mean negative 6. Is it negative 6? So I'm here, 36, so 0.000036. I'm backing up 1, so I should be backing up 1. Thanks, Taz.
No, I said like 3.9 times 10 or something. I don't know.
Yeah, I was just estimating. Okay, so regardless, we know the process is multiply. Woo! All right, what happened to the K value? It got smaller. So we know that this is, still the reactants are favored, but in this case, the reactants are super, super, super favored in this reaction because it's very, very, very small compared to these two. Okay, can you write the K expression for this first one? Let's call this 1 and 2. What's the K expression for 1? C2H04 negative times H plus. If I'm not giving you states of matter, let's assume they're all aqueous or all gases. Okay, so keep going. Over what? I hear you. I'm just struggling up here. Okay, over C2H2O4. Okay, I'm taking the Kc and I'm multiplying it by the Kc2, correct? So technically, what am I doing here? I'm taking this and multiplying it by the other. Okay, so what's the other? H plus concentration times oxalate over. Okay, simplify the multiplication of these. Simplify that. Cancel out what? This one? Huh. Isn't that what we did up here? Okay, so when you simplify and you crunch it together, what else simplifies? The hydrogen ion becomes to the second power, because it's 1 plus 1 is 2, times oxalate over, C2H2O4. And by golly, this represents this. Doesn't it? Yeah? Okay, so it should, because this K and this K, when you mesh them together, something's going to cancel like we had up here, and that cancellation should yield the same products and reactants as this reaction here had. So this is K3. Okay, I'm going to stop for now, okay? I need to quickly modify parts of homework. All right, so please write down textbook page 687. You are doing the first 6 and question marks anything we get there? I like to make sure I know what I'm doing here. 6 weeks. Alright, you are totally qualified to do 6, 10, 21, 22. Lost it. 23. You can do 23. You can do 24. You can do 25. Can you do 27? Yes, you can. Can you do 31? Yes, you can. Okay, we're good. Okay, yeah, except for those, I was just making sure I was in the right place. So our graphs are done, right, from our lab. And the questions are done from the lab. Yes. Okay. All right, so I'll see you guys at intervention. We'll chat about phonetics, and then we'll move on from the phonetics. Not yet. I still have to score them. I'm waiting on theirs. Hey, can you stick it in there? Yeah. Thanks, guys. I'm here until 3 o'clock after school if you want to hang and talk about chemistry. Not just hang.